negative. The easiest way to do that is with a negative 1 to the n in front.
Okay.
So if you have negative 1 to the n, as n goes through 1 to 2, it's going to go negative 1 to the first, then negative 1 squared, then negative 1 to the third, dot, dot, dot. So that's going to go negative 1,
Okay.
positive 1, negative 1. So by multiplying by that out in front, that's going to cause it to oscillate between positive and negative.
Okay.
But you said you were good
How
on
do
the
you?
rest of the pattern, or?
Yeah. How do you do the other way though? Like negative positive, because that's how number 19 is, and it has negative 1 to the n plus 1.
Right. So if I don't want the first one to be negative, I want the first one to be positive, I have to start, because technically we could go either way. So if I don't want it to be negative 1 to start with, I either have to start I have to start on an even number. However, when we do our
Oh.
as you do your series and your sequences in series, remember I told you guys you always start at n equals 1.
Yeah.
Well, if n
So 1
equals
plus 1 will be
1,
2.
I either have to add 1 or subtract 1. Technically, you could add pretty much any number. So if I wanted, really, I could do n, instead of plus 1, I could do n plus 3. I could do n plus 5, n plus 7. I can do any number I want up here as long as it causes this one to start out being positive versus negative. So you could do n plus 3. Most people just do n plus 1 because it's the easiest case. You also could do n minus 1. If you want to go backwards to the 0 power, that is also perfectly fine. But any of those three that I have up there, they will cause you to have a positive starting
Well,
value.
couldn't you only do to the n minus 1 if you wanted it to equal 1, because anything to 0 is 1. It would like, so if it was like negative 3 to the n minus 1, then it would just be 1.
Right, that's what I'm saying. It just depends on which one you're doing. But typically, you
Okay.
don't. If we're just trying to do the oscillating part, you just have a negative 1 in there, not a negative 3. In other
Okay.
patterns and stuff like that, you can have a negative besides 1 in there. Um, but it just, yeah. So you can go either way, really.
Okay.
And it just depends on what your starting value and everything is. But yes. Any other questions from the homework from anybody on anything they need me to do?
I have a question.
Why am I not surprised? God, Brisa.
Oh my god. Okay, listen. So, I accidentally forgot that we had class yesterday.
Okay.
And where would I watch like a video of
YouTube.
what YouTube?
Yes, I have all my videos uploaded to YouTube. I sent you guys a link for the YouTube channel. I can send it out again if you need me to.
Can you please later
I will,
whenever you have the
yes.
time?
You'll have to
Thank
remind
you.
me because I'll have class for a little bit
And
after this as well.
what are we doing today again? Just
Second part of
reviewing.
19.
Okay, so okay, got it.
Yeah.
Thank you.
You're welcome. Any other questions from the homework or anything before we start? Okay. So we've defined recursive. Okay, so we left off at partial sums. Okay. Partial sums are pretty much exactly like they sound. It's a sum of numbers. So we talk about a series. Remember I told you yesterday, so let's say we have the sequence 1, 2, 3, 4, dot, dot, dot. That is called a sequence, as a reminder, just from yesterday. So if it's just a set of numbers kind of going in order, that's what we call a sequence of numbers. When we talk about a series of numbers, we are adding those numbers. Now, here's the thing. Does that sequence of numbers ever stop?
Doesn't depend.
Looking at what I have on the board, does that sequence of numbers ever stop?
I can't see it yet.
Oh. How far back is your stream?
My computer froze.
Oh, that's not good. So somebody else besides Madeline then that can see the screen.
It doesn't stop.
How do you know it doesn't stop?
You have the 3 dots after it.
Okay, so I have the
Yeah,
three dots
you
after
didn't
it.
write A to the N on the other.
Even if I write an A to the N, so even if I wrote like A sub N, does that determine that it stops if I have an A sub N at the end? And that answer would be no, because N could go forever. Now, if I have a number at an actual number, like let's say 15, if I put 15 there, then does that sequence of numbers stop?
Yeah.
Yes. So if we have the dot dot dot, which bonus points, anybody know what the dot 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 is?
Oh, forgot what it's called. I used to know what it was called.
Does Abby have it? No, that's not called the numbers in between. It has a name. It's actually a really coincidental name.
I think Mia knows it.
Claire, the question was, what's the dot dot dot? It has a name. Mia, Madeline says she thinks you know it.
Yeah, she said it.
I didn't hear what you said, sweetie. You were very quiet.
Ellipses.
Oh, that is correct. And Claire, good job. It's called an ellipses, which is very ironic because we just did ellipses as a thing, as we graphed them. So an ellipse, or ellipses is the plural. That's called an ellipses in English. Different word, different meaning, obviously. But yes, it means goes on forever and ever, or if you have something on the other end of it, it goes on until you reach that thing. So if I don't put a number on the end of it, that means it goes forever. Well, here's the question. Can you add 1 plus 2 plus 3 plus 4 plus dot dot dot? Can you add that all together? In other words, can you add an infinite number of numbers together?
No.
Do we agree with Miss Madeline? Is the answer no?
Yeah, you can't.
Okay. I'm here to tell you, you can. I know, right? This problem necessarily no, because these numbers keep getting bigger and bigger. I cannot add an infinite number of these numbers. There are sets of infinite numbers we can add. We'll get to that later. So I can't add these together. So what we do instead is we do what's called a partial sum. A partial sum is where we add up just part of it. So in other words, I could have, and this is denoted as S sub n. That is a partial sum of n, or of the first n numbers. Of a sequence. So if I want a partial sum, in other words, I could have a S sub 4, S sub 5, S sub 6. That just tells you to add up the first 4 numbers, first 5 numbers, first 6 numbers, etc., etc. Okay, does that make sense? Hopefully it should be pretty, that definition is usually pretty easy. 7, 10, 13, 16. Okay, so I will leave the definition for a second for Navee's still writing. So we'll start off really easy. We're given a sequence of 7, 10, 13, 16, dot, dot, dot. We'll start pretty easy. Like I said, just do the first S sub 4. So how do I figure out S sub 4?
You add them all together.
Define all.
The first 4 terms.
Okay, so add the first 4. So pretty easy, not a big deal. I don't feel like doing math in my head right now, even though it's not too bad. 46. So that's literally all a partial sum is. Not too bad. You could do S sub anything. The question is, if I want what we call S sub k, in our case, or you could do S sub n or whatever, what I'm asking for at this point when you see S sub k is a generic formula for the sum of any number. So I want to figure out, how do I figure out what this sum is in terms of a generic formula? Okay, well at this point, what we're going to do is we're going to kind of fill in everything. So we get 7 plus 10, we're going to use what we just did, plus 16, plus, we can put a dot, 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 and then plus what? What is my last term going to be?
Okay.
In order to do this, we need the general term. So it's going to be plus whatever a sub k is. should know. So we need to figure out what is this last term, a sub k. That's my last term. Remember from yesterday, our last term was like a sub n, and we figured out what that last term was. We need a generic term. So how do I figure out what my generic term is? This is going to go back to what we did yesterday.
The pattern.
So we're looking at our pattern. So again, if we do it the same way we did yesterday, we get a sub 1 is equal to 7, a sub 2 is equal to 10, a sub 3 is equal to 13, and then we're looking for, okay, we need to figure out what is a sub k. You can call it a sub n if you want to, it doesn't really matter. There. So I need to figure out what is the pattern from 7 to 10 to 13. And we want to be careful, we don't want a recursive algorithm. So the recursive algorithm here is a really easy one. It's, add 3 to the previous term. That doesn't do us any good because we don't want to have to calculate the previous terms. We want to know what that generic term is. Oh, yeah. Good job, Abby. But yeah, we don't want to use that one. So this one is a slightly harder one. So you got to be careful. We want to figure out, we do notice we're adding 3 each term, so that's fine. So it will be something plus 3. I'll give you that hint. So anytime you do have that recursive part, it's going to be included in your equation. So you do have something plus 3, plus 3, plus 3. We got to figure out what is that something I am adding to, though. To give you a little hint, that's going to be, we can't put that in yet. So 4 plus 3, 7 plus 3, 10 plus 3, et cetera, et cetera. So what I'm looking for is, how do I get a pattern between 1 and 4, 2 and 7, 3 and 10, and then k and whatever we'll get. So that's the pattern we're looking for. So that's how I'd break this one down. Since I know I'm adding 3, I can do it that way. Well, pattern between 1 and 4. How can I get from 1 to 4? Just start listing off ways.
Add 4. Or no, sorry. Add 3.
Okay, so I could do, one possibility is 1 plus 3 plus 3. That would mean this one would be 2 plus 3 plus 3. Is 2 plus 3 plus 3 equal to that?
No.
The answer is no. So that way doesn't work. I'll give you a hint. Adding usually isn't the option. Sometimes it works, but not very often. So how else can I get from 1 to 4?
Multiply by 4.
Multiply by 4.
That's not gonna work. Then.
So clearly doesn't work there because 2 times 4 is not 7. So this one is slightly more difficult. And I'll give you kind of, I'll go ahead and give this one to you. So it's actually 3 times 1 plus 1. 3 times 2 plus 1. 3 times 3 plus 1. 3 times k plus 1 plus 3. Oop, I forgot the plus 1. So what we have to realize is this is always 1 more than 3 times the number we're dealing with. That is not an easy pattern to get. So again, I know this. Plus 1. Oop, plus 3. So don't, like I said, this is not, oh, you should know this. This is super easy type thing. This is, seeing that pattern is not an easy one. So just realizing that if I do 3 times that plus 1, it's always 1 more than 3 times that number. Is that an easy pattern to find or see? Definitely not. So it ends up being 3k plus 4. But these are just patterns you gotta look for, multiplying by numbers. Like I said, usually adding a number is not gonna be it, but things to look for as you're making notes to yourself, always look for things like squares. If you're squaring it, multiplying by a specific number. In some cases you do multiply by a number then add something. So Again, I know it's frustrating if you don't see the pattern, so I do sympathize and I do understand. It's not always easy things to do. And don't think I can just do them all, because there are some that I struggle with as well. Sometimes they're not easy. Okay, so now after we get our generic term, we can actually go back and put this in up here. So plus dot dot plus 3k plus 4. 16. Does everybody, again, I'm not asking if you would be able to do that on your own, but does everybody see how I kind of got that pattern of picking out those numbers? I like Abby's answer because Abby's answer is very apropos. Yes and no. I do understand, like I said, it is difficult. I'm not saying necessarily could you do that on your own no matter what pattern I give you. It's just kind of, do you see some of my thought patterns? Because that's the best thing I can teach you for seeing that, is just kind of what I'm thinking as I'm looking at these numbers. Since I knew it was plus 3 each time, I could pull that out. And then I have to find a connection between what's left type idea. Now, with that, we have, instead of writing this out, because this is not a very nice and neat way to write this out, because this becomes very long and tedious, we actually want to have a shortcut to writing out our sums. And we have that, and it's called summation. I think I spelled that right. Notation. So we have summation notation. Yeah, okay. Our summation notation is a Greek letter.
I saw that in the homework.
Yes. I equals, we'll say 1 to 7 of a sub I. Okay. So as we look at them, each part has its own meaning. Does anybody know what that letter is by chance? Nobody? Nobody knows that letter?
I don't remember it from Latin. I know we did it, but
You do cover it in Latin, that is true. Usually other people know it because of fraternities and sororities. And yes, Miss Claire, that is correct. That is a sigma. Usually I get people from the sororities and stuff like that that have parents and stuff, and then that know at least one or two usually does. This is a Greek capital sigma. And all it means is, that's a terrible, sum. So that means we are adding something. Okay. Actually, I'm going to move this over some so I can. It would help if I can spell correctly. And it means sum. We have our I down at the bottom. This is what we call our index. That's why it's an I. Start or lower bound. Whatever the index is equal to is what we call our starting point, or what I refer to as a starting point. It's also called your lower bound. The number on top is then obviously your end or your upper bound. That's a terrible bound. And on the inside, we call that's our term. So in some cases, you'll see it written like that, and we'll look at some other ones where it's not written quite like that yet. But that's what we call our generic term, our general term. So instead of saying like A, before we said A sub k or A sub n, that is going to be our term. Now, sometimes you'll see this written out as multiple different ways. Also, I will never write my E like that because that takes too much time and effort. The E that I will always write will be like the one on the bottom.
What is the word next to or upper bound?
End, E-N-D.
Okay.
So again, I will never write the E out the way you see it up there. It takes way too much time and effort. Instead, you'll see my E's that look like that. So that's my sigma. So if we do the same way we have here, so I is equal to 1 from 7, A sub I, A sub 2. Not Z. So the sigma notation that I have written on the board would be as such, to where that basically tells you add the first 7 terms.
So this is only for series?
Yes, this is for series. So it's what we use it for summations is just, I mean, really it's used for summing up anything you want, but it'll be like that. Now, sometimes you'll see it with a notation like we're used to. You can also see it with things like a, so I equals 1 to 7 of I squared plus 3. You can also see the generic term written out for you like that. So in this case, we start at I equals 1. So my first term, my A sub 1, will be 1 squared plus 3, which is, I'll write it actually out so on our first one. So 1 squared plus 3. My second term will be 2 squared plus 3. And then 3 squared plus 3 plus 7 squared plus 3. Does everyone see how the sigma notation works? That makes sense, hopefully.
Will it always be 7 up there, or can the 7 change?
It can be any number I want, whatever I want to end at. So I just picked 7 in this
Oh.
problem. I kept it 7 the whole way through, so it's the same kind of stuff.
Wait, so in the previous problem we did, would you use that notation?
You can use it. You don't have to, but you can, yes.
What's the purpose of using it?
What happens when your notation becomes like 500? What if I want to know how I'm doing that? So I don't want to have to write out those terms, so it becomes much easier to write it out like this.
Oh, okay.
It's a quick, concise way of writing things out. Instead of writing out a partial sum, being like, oh, it's this plus this plus this plus this plus this, we just write this out, and we know that means add up the first 7 terms. So you go 1, 2, 3, 4, 5, 6, 7, plug that into your formula, and add them all up. Does that make sense? The notation and how we write things out. Make sure, like I said, it's pretty easy, straightforward. You just got to know how to use it. It's not too difficult.
So for the answer of like the partial sum, you could just write out the E with the stuff on it. Like the 7 and
yes,
the I equals 1 and the...
That is something they could have you do. They could have you say, write out a partial sum as a summation notation to make sure you know what each piece is, where the pieces go, and things like that.
Okay.
So that is something they definitely can do.
Can you write it out for the problem we just did earlier? Oh wait, you erased it.
I already erased it. I don't know what it was. But it'd be pretty much the same thing. You just plug in the generic term and then put your I equals 1, I equals whatever, like 6 or 4 or K.
Yeah, what is I? Like, how do you...
I is your index, and we'll talk about that in a second. You'll see a problem where I use something other than I. But I is just your index, so it increases by 1 each time. So notice how my I went from 1 to 2 to 3 to 4 to 5. Just like we talked about before, you have your first part, your second part, your third part, or term, sorry, first term, second term, third term.
That's like the N.
Yes.
Okay.
And if we want to, we'll do a couple examples real fast just to make sure we can do them. We can use things other than I. You can use pretty much any letter you want to. Typically, we tend to use I because it does stand for index. But you see other ones such as like K and stuff like that. So for instance, if I do the ones in the book, I think it's 6 I squared. And then we have the summation of K equals 1. I forget what this one was. 1 to 5 of K. Oh no, sorry. Negative 1 to the K over K. So notice here 2 different problems. I can use I there, I can use K there. The important part is when you look at this, what do you know that you're doing on this type of problem?
You're finding the first, like, blank term.
Careful, that is not the correct answer. What is this problem telling me to do?
Does it write out the sequence?
Nope.
Do you add to the first blank term?
Correct, because what does this Greek letter mean again? Sigma means sum. I am adding. This is a summation, so we are adding up the first blank terms, in this case from 1 to 6, on the first one and 1 to 5. So when we do the first one, summation from I equals 1 to 6 of I squared, I start at 1, so I plug 1 in, and I get 1 squared. Then I move to the next one. After 1 is 2, I get 2 squared, and 3 squared, 4 squared, and I stop at 6 squared. Okay. I'm not going to take the time to write that all out and add those up because I don't feel like adding them. I'm sure you guys can all enter that into a calculator. When I do the second one, though, the only thing that changes is what? Well, besides the formula. But what's the difference on the second one to the first one?
You only do 5.
It's gonna be the alternating thing, right?
It will alternate, but what's really different? So instead of going from 1 to 6, I go to 1 to 5. Yeah, the formula is different. But the important part is, what am I changing on each next term? What's the changing value?
Okay.
K. So you can have more than one variable on the inside, so you could have x's and stuff like that as you start to get to more, but you have to understand what number or what thing is the one that's changing. In our case, it's going to be K. So when I do this, every time I go to my next variable, or my next term, the K value is going to increment by 1. So the first one will be -1 to the first over 1, plus -1 to the second over 2, plus -1 to the third over 3, to the fourth over 4, -1 to the fifth. As already mentioned, and we talked about earlier, that -1 to the K power being on top will cause it to alternate, and that's perfectly fine. And then you just add or subtract all those up. And your calculator can do that for you, obviously. Then you can hit math fraction and keep it in a fraction form. We're not asking you to show out all the math as far as that goes. Showing out that step and then using your calculator from there would be perfectly fine. Is that making sense, hopefully? I'm not getting a lot of responses from people.
Yes.
Yes.
You've been responding, Madeline. You're good. Okay. All right. I am not going to write all of them out. Okay, these I will. Never mind. So with our summation notations, we do have some notational things and some properties that we can use with them. So the first one is summation from I equals 1 to, what do they use, n? Make sure I use the same notation as the book. Yeah, n. Okay. So if I have this notation, so summation from I equals 1 to n of c, yes, that can change, Abby. We'll look at some problems. I'll make sure we do somewhere it's not 1. But what does that mean I'm doing? So what do we think C is going to represent? Because clearly it's not I. So what do we think C represents? What do we use the letter C
constant?
Yay, constant. So it's a constant. Anytime you see the letter C, always think to yourself constant for the most part. So I am adding up a constant over and over. So what would that summation look like? So if I is equal to 1, what value do I get?
One.
How'd you get 1? So think about before. Hold on. Think about before. When I was equal to 1, what did I do with that I value? Last example, what did I do?
The last one you squared it? No, the last one you...
Not specifically what did I do. What did I do with that first value? Give me some sort of verbiage that tells me what I did.
added?
Before that.
I don't know. Someone else needs to say something.
So we knew that k was equal to 1 on the first term, right? What did I do with that 1? Look back at the last question. When k was equal to 1, what did I do with that 1 to figure out the value?
You put it into the formula?
That's a correct verbiage. I would have accepted also plugged it in or substituted. You plug in the value for I equals 1, then I equals 2, then I equals 3.
But there's no I in the formula, so...
So what does that mean I'm going to get when I plug in I, quote unquote?
0? 0.
No.
1?
I get C. No matter what is my value always going to be?
C.
C.
C. What about when I plug in I equals 2?
C.
What about I equals 3?
C.
I'm going to get C every single time. In case you're confused on how I got that, think of the equation y equals 4. If I do a t-chart and I plug in 1, 2, 3, 4, 5, etc. for x, well, there's nowhere for me to plug in x, so what do I get from my y value every single time? I would get 4. Same value I'd get every single time. So no matter what x is, I always get 4. It's the same thing here, except for it's some value c. I don't know what that c is. Well, the question is, how many c's would I have?
Infinitely many.
Nope.
No, until n.
I would have n of them. Very good, Miss Madeline. Well, if I have c plus c plus c plus c plus c plus c plus c n times, what's an easier way of writing that out?
N times c.
N times c. And we're going to call that cn. That's what we typically refer to that as. So if you add a constant over and over and over and over, we have a very easy formula to figure out that summation. So this could take a very long process where I'm adding it up 500 times. Instead of doing 500 calculations, I can do 1 calculation. Okay, so that is our first property. If you're adding a constant multiple times, you get that. So this is like property number 1. Number 2. So if I have a constant c times a term, and it doesn't matter what that term is, we're going to call it a sub I. What would that summation look like? So what would my first term look like? Let's call in some people because people aren't answering. I'm going to start at the bottom today. Sydney, what would the first term be?
Yeah, I have no clue.
How do you find the first term?
Oh no.
What did Miss Madeline, would you please refresh everybody's memory what you said last time? How do we find the first term?
Plug it in.
It is not a word we can use.
Okay, you said that was an acceptable answer last time.
because I was being nice. But what are we plugging in? We can't use the word it. What do I plug in?
Plug I in.
Be a little bit more specific.
Plug the value for I in. So if I equals 1, then you plug 1 into I.
There you go. So if I'm on the first term, Miss Sydney, what is the value for I?
What? I don't know.
Yeah, 1. No, you're good. Yes, 1. I'm not trying to be mean or trick you. It's 1. So if I plug 1 in, what would that look like, Sydney?
Where do you plug it into?
I?
It already says I is 1.
No.
That's why.
The summation, remember, you got to be careful. Your summation notation tells you where to start. It does not say I is equal to 1. That says you start at I equals 1. And then I stop when I is equal to n at the top. So that tells me my first term, I equals 1. So how do I find the first term?
You plug it in, I guess.
Don't use the word it.
You plug 1 in, but I don't know how. Like, I understand that you put it there, but what math do you do with that?
There is no math, sweetie. You just plug 1 in.
Oh, then plug 1 in.
There you go. So I replace every single I, or substitute, or plug in 1 for every single I. Okay, Mia, you're second. What's the second term, Mia?
C a sub 2. Is that how you say it?
That would be very good, yes. And what are we doing with C a sub 1 and C a sub 2? What is it?
Adding.
So it tells me to add. Mallory, what's the next term? Hoping people are seeing the pattern by now, so it should be quick. Mallory. Maybe Mallory's using the bathroom. We'll give her a break and I'll come back to her. Madison, what's the third term?
C a sub 3.
Oh man, I don't know how you figured that out. I don't
I'm
know.
just that smart.
I think Madeline's next. Madeline, what's the next one? Madeline.
Sorry, I was muted. C A
okay.
sub 4. I said it like 5 times. I was like, why is...
So CA sub 4. I'm assuming by now everybody's noticed the pattern. Yes?
Yeah.
Okay, Jason,
Yeah.
you get the unlucky part. What's the last term? Because you can't just follow the pattern anymore. Jason. Okay. Well, I didn't know if you were there or not, so I just want to make sure. I'll give you a hint. The first term you plugged in 1. The second term you plugged in 2, etc., etc. What are we plugging in for the last term? How did you get 5 to be the last term? Can someone help me out? How do we know what the last term is?
It's C a sub n.
the top.
Thank you for giving the answer, not helping, Madison.
Sorry.
Thank you, Madeline, for giving a great help. The last term is determined by the number on top. So n is the last thing we're plugging in. So if I plug in n, Jason, what do we get? So just like on the other ones, you gotta be careful, buddy. If you plug in 1, plug in 2, plug in 3, plug in 4, my last one will be to plug in n. So it'll be C a sub n. Does everybody see how I got those terms as we're working through them? Hoping by silence the answer is yes, because if you're not, you have to ask questions, peoples. Okay.
What was it? My computer is completely broken down right now. I don't know what happened. So I'm using my phone.
I'm asking if people are understanding how I got those as we move through them. That's why I'm doing multiple examples out the long way, so people see how I
What
get
was
all these
the
things.
yeah? But what was the final term?
C a sub n. So you just plug in
Okay.
n because n is your last term. You don't know what n is, so you just leave it as n.
All right, my computer stopped working, so I will have to be using the stream on my phone.
No problem, buddy. So the question now is, we should see a pattern of something that has happened to all of those terms. What do we notice about all of those terms? What can I do to them?
Multiplied times. Oh, never mind.
So you're good. No, say what you were saying. You're right.
You can. They're all multiplied times c, so you can like distribute out the c, undistribute the c. Sorry.
Let's use a better word than undistribute, please. Somebody help her.
Factor out.
There you go. So we get c times a plus 1, or a1 plus a2 plus a3 plus a3 plus an. Well, I really don't want to write all of those terms out. So how could I rewrite a1 plus a2 plus a3 plus a4 plus a5 a sub n? So how can I rewrite this sum of a very long sequence of numbers?
The partial sum.
That's not a wrong answer, but what's a quick, short way of writing out a sub 1 plus a sub 2 plus a sub 3? How do I write out a sum of numbers? How do I write out a sum of a string of numbers, people?
Sigma?
Which is called what? It has a name. It's 2 words.
Summation notation.
There we go. We can use our summation notation. Thank you, Miss Madeline. So this is nothing more than a sum, and I can write that out as the sum. Where does my summation start? At which term? So what number do I start at?
1 or
1.
a sub 1.
No, so I start at 1. So I equals 1. Where do I stop? I stop at n. And what is my term? All of these terms in this case are a sub I. So what I do is I take c, multiply by the sum of a sub I. So if I want to make a quick jump from my first line to my last line, what's the quick and easy jump that I can do?
Is it C times A sub n?
Well, no. So first line to last line. So some sigma from 1 to n of c a sub I to the last line. What did I change?
Just move the c out front.
So I'm allowed to move my constant, if I'm multiplying by a constant, out front. And this is the why I am allowed to do that.
Because it's always going to be the same, right?
Because I will have a c in front of every single term, so I'm factoring it out. Do we need to do it the long way every time? No. That's the point of having these rules and seeing why they work, is so that I can use them very easily. Okay. We will finish the lesson there, but before you leave, there's a couple of